All right, we are working on page 2 of GLA3, working with solving quadratic equations. Question 6 says solve, and the hint says set the trinomial equal to 0 first and look for a special product pattern, such as a perfect square trinomial, hint, hint. Okay, so we are going to follow the advice of the hint and set it equal to 0 first. So how do we do that? We are going to first get some ink, and then we're going to write the problem. 4x squared plus 25 equals 20x. Now, if I want to set this equal to 0, I can subtract everything from one side of the equation, making sure to also subtract it from the other side, leaving nothing on one side and everything else on the other side. So this 20x on the right minus 20x zeroes out, which is what we wanted. We wanted 0 on one side of the equation. And then we have 4x squared minus 20x plus 25 equals 0. Okay. Now I'm going to look for a special product pattern, such as a perfect square trinomial, as the hint suggested. Well, what is a perfect square trinomial? I'll give you an example of one. I'm going to do this like the other way around. You've learned at some point how to multiply two binomials using the FOIL method or the distribution method. Two different ways of saying ultimately the same thing. That's where every term in the first binomial has to multiply every term in the second binomial. So it's kind of like you start with 2x and multiply it times 2x plus 3 quantity. And then you're going to take the plus 3 and multiply it times that whole second quantity. Okay. And the 2x times 2x gives you 4x squared. Okay. Now notice that though that 4x squared is a result of multiplying the first two terms, the first terms in each binomial. So that is where the f in FOIL comes from for the firsts. Then when we go on and multiply 2x, distribute it over to the positive 3, then we get positive 6x. And you might notice that what we just did there was we multiplied the 2x times the 3. Those are the two outer terms, so that's where the O in FOIL comes from. Moving on, we're going to multiply the 3 times 2x so that we get another term of 6x. And notice that that just happened because we multiplied the two inner terms. So that's where the I in FOIL comes from. And spoiler alert, this is going to be the two last terms. When we multiply the positive 3 times the positive 3, those are the two outer terms, and we get positive 9. And that's where the L comes from because those are the last terms in each of the binomials. All right, so now notice what just happened here because I multiplied two binomials that were identical, which is what happens when you multiply two numbers that are identical, right? 3 times 3 is 3 squared, right? 4 times 4 is 4 squared. And 2x, the quantity 2x plus 3 times the quantity 2x plus 3 is really 2x plus 3 quantity squared is another way of writing it. And so when you're squaring a binomial, it results in what we call a perfect square trinomial. The trinomial part of it is when you combine those two middle terms, and then you just have three terms. And that makes it a trinomial, but what's interesting about the pattern is that that middle term, those two middle terms, are always identical. So you get a duplicate. 2 times 6x gives you 12x, right? 6x plus 6x is 12x, or you could say 2 times 6x is 12x. So notice what's going on here. If you were to take the square root of this term, you would have 2x, right? And that is the first part of your binomial that's being squared. And if you were to take the square root of positive 9, you would get 3. And that is the second part, second term in your binomial that's being squared. And then the middle, what's interesting here is the middle two terms are 2x times 3, right? 2x times 3 is 6x. But you just have a duplicate of them. So it's 2 times whatever the square root of each of the outer terms is. So we're looking for that kind of pattern here. That means that if your middle term is not even, if it doesn't have an even coefficient, it's definitely not going to fit the perfect square trinomial pattern. And what we want to do is just see if this trinomial could be factored into a perfect square, meaning could be written as a binomial that's squared. If it is a perfect square trinomial, we can write it kind of like you see this one written, a quantity, binomial quantity squared. So we're looking for that same kind of pattern. And since you know you had to have two identical terms resulting from squaring a binomial, if that middle term is not even, it can't possibly be a perfect square trinomial. Now we do have an even coefficient on our middle term here. Let's divide that by 2 and see what we get. Because we so far have the square root of the first one would be 2x, the square root of the last term would be 5, and then multiplying that together would be 10x, and that, if doubled, would be 20x. So it fits the pattern. That means that this trinomial can be rewritten. Instead of writing 4x squared minus 20x plus 25 on the left side of our equation, we can write it as 2x, we're taking this, 2x, and then since this is negative, we want a minus, then we're going to take this, 5, quantity squared equals 0. And if you wanted to test it out, which I encourage you to do so, you could see what happens when you multiply the quantity 2x minus 5 multiplied by itself. If you FOIL it out, you get 4x squared, then negative 10x, then negative 10x again, and then positive 25. And there you see the twins in the middle. When combined, give you the negative 20x. And this is the original polynomial we started with on the left side of our equation. Okay, so why do we want to do this? Because once we have the trinomial written in this way, we can take the square root of both sides to get rid of this 2, the power of 2. So if you want to undo a square, you take the square root. Right? So we're going to take the square root of both sides. We take the square root both sides, and we end up with 2x minus 5 on the left. And then we have to remember something very important. Whenever you're taking the square root of both sides of an equation, you have to put a plus minus on the side opposite the variable. If you forget that, you're going to end up with only half of the answers you should have sometimes. So just be careful. Now, when it comes to taking the square root of 0, it turns out that the plus minus doesn't become very important because, of course, the square root of 0 is 0, and whether you have positive 0 or negative 0, it's still 0. So it works out in our favor. When you take the square root of 0, you just get 0. All right, so now we just have one equation to solve, and so we're going to add 2 to both sides. Oh, sorry, no, didn't mean to say that. We're going to add 5 to both sides. And and then we'll have 2x equals 5. Then we're going to divide both sides by 2. So 2 divided by 2 is 1. 1 times x is x. And then we have our answer, x equals 5 halves. Now we know that with quadratic polynomials, we can sometimes and often do get two distinct different answers. This would be a case where we have one repeated root, one solution that is working for both factors, in other words. So it is okay. Sometimes you get a single answer, and that will be the case anytime you're working with a perfect square trinomial. So that's the answer for that one. What did I say it was? 5 halves. Right, next, this just says to factor. Now, we're in the Department of Special Product Patterns, and right away I noticed that this was a special product pattern. Special product patterns are just ones like that perfect square trinomial pattern that if you get familiar with them, you become kind of an expert in factoring. You're able to factor very quickly and find the solution with almost no effort eventually, once it becomes, something you really understand. So if I want to factor this, and I'm looking at the fact that there's only two terms, I can't factor out a GCF really because 9 and 64 don't have anything that divides evenly into both those numbers, so I can't factor anything out of the number parts. And I don't have any x's in my second term. So that leaves you kind of stuck if you're trying to factor, unless it fits a special pattern, which I suspect it does. So there's this pattern called the difference of squares pattern. And when you see it, it makes factoring really easy. So the easy short way of saying it is that a squared minus b squared factors out to a minus b times a plus b. This could also be written as a plus b times a minus b. It doesn't, the order of the factors doesn't matter. As is the case anytime you're multiplying. Multiplication is commutative. It can go in either order. So now I want to see if I can use this special pattern for this polynomial. So I'm looking for two things. I'm looking for the first term to be something that I can write as a perfect square. And I can write 9 as 3 squared, and I can write x squared as x squared, so 3x quantity squared. That would be like my a in this, my a squared. So a is the 3x part. Then 64, if you take the square root of 64, you get 8 because it's a perfect square. So I can rewrite 64 as 8 squared. And that fits the perfect square. I'm sorry, I almost said the wrong thing. That fits the difference of squares pattern, which means that I can factor 9x squared minus 64 and rewrite it as 3x minus 8 times 3x plus 8. Or I could have also written it as 3x plus 8 times 3x minus 8. And that's it. That's all you got to do for that one. Next, question 8. We have several polynomials to factor here. And let's read the directions. It says, solve the following quadratic expressions by factoring. First, write the expressions completely factored, then write the real number solutions. Hint, remember to use proper notation when writing the real number solutions. For example, if your solutions are x equals 1 and x equals 4, then write x equals 1 comma 4. Also make sure that you write out each factor separately. For example, if it factors to x minus 1 times x minus 1 equals 0, do not write it as x minus 1 quantity squared equals 0 will be marked incorrect, even though it is technically equivalent. Okay, noted. So let's go on and start to work through these. So first I have x squared plus 13x plus 42. X squared plus 13x plus 42. Now what we want to do here is find, well, first of all, I'll make the note that since the lead coefficient is 1, I already know that the two binomials it could factor into would have lead coefficients of 1x. And if I multiply the a times c here, a is 1 and c would be 42. So the AC method would also yield 1 times 42 is 42. And then I'm looking for a sum of the middle term, positive 13. So I am seeing that since the product is positive and the middle term is positive, both of my factors should be positive. So I'm going to have plus in here and here. Now I'm looking for two numbers that multiply together to give me 42 and add up to give me 13. The first thing that popped in my head was 6 times 7, and that does work. It adds up to 13. So 6 and 7. And remember, it was set equal to 0. Then we were supposed to solve it. So now our solutions will be x equals negative 6 and negative 7, right? Because you would have set each one of these equal to 0 one at a time and then subtract to get x alone. So that's why we end up with the opposite signed values. And notice that if you plug in negative 6, you'll get negative 6 plus 6 equals 0. And then 0 times anything is 0. So that would make the statement true. And also, if you were to just plug in negative 7, then this term would this factor would 0 out and the whole left side would 0 out as a result. So that is the pattern here. We got our answers. We have both the factored form of the equation and then the actual solutions written out. Pause. Okay, I just entered those and made sure it was marked correct. Now the next one, I think I can work without actually writing things out now because, again, we see lead coefficient of 1 here. So I know that if it's going to factor out, it'll factor out to two binomials that both have x in them, and it's going to be equal to 0. And then the left side, I still have to add and subtract or add or subtract numbers. So to get a product of negative 30, I would have to have two opposite signed numbers. And the first thing that popped out in my mind was 5 and 6, which 5 times 6 equals 30. And if I do a positive 5 and a negative 6, then when I add positive 5 and negative 6, I get that negative 1. That would be the the coefficient of the middle term. So that's how it would be factored. The real number solutions would then be x equals negative 5, because if you plug in negative 5 to this factor, it'll 0 out. Or another thing that would work is if you plugged in positive 6, then this factor would 0 out. So we would have these two answers. This one right here is a perfect square trinomial, right? Because I can see x squared is obviously a perfect square. 49 is 7 times 7. So being that it's a difference of two perfect squares, I can write this as x minus 7 times x plus 7 equals 0. And then the solutions would be x equals negative 7 comma also positive 7. Okay, now the last one on this question, again, a lead coefficient of 1, that's helpful. So I'm looking for two numbers that would give me positive 16 when multiplied, but negative 8 when added. So that would mean if I have a positive product, meaning, when you multiply, you get something positive, they have to be the same sign. And since the middle is negative, I know they're going to both be negative, right? So I already know it's going to be x minus something, and then also x minus something, okay? I also noticed that x squared is a perfect square and 16 is a perfect square. And the square root of x squared is x. The square root of 16 is 4. And if I do 4 times x times 2 and double it, I get the middle term. So this is a perfect square trinomial, actually. It's going to turn out to be like this, where the two factors are identical because it's a perfect square trinomial. Remember, take the square root of the first one. Maybe I need to write this part of it out. Here, I'll come over here and we'll just do a little writing to kind of connect it back to what we were doing before. Remember, x squared minus 8x plus 16. I go, ooh, I see a perfect square right here. That square root is 4. And of course, the square root of this is x. And then if I multiply those, I get 4x. And if I double that, I get 8x. So there you go. Then also because there's a minus here, that would mean that the whole trinomial would factor to x minus 4, quantity squared, or in this case, just because we were told to write it in expanded form, we're going to write it like that. Okay, perfect square trinomial. And then there's only one real number solution, which is 4, because they're identical. Okay, number 9. We're going to solve 5x squared plus 17x equals negative 6. Now, you may have noticed something. Hopefully, you've noticed that in anytime we've been solving a quadratic equation by factoring, it's been equal to 0, or we had to set it equal to 0 first, and this is no exception. We're going to have to first get it set it equal to 0. So I'm going to add 6 to both sides. That way, the right side of the equation will 0 out. And then I'm going to make sure to write my terms in order by degree, meaning that the powers on the x's go down largest to smallest. And now I'm ready to start trying to factor that. And I'm going to use the AC method. A would be 5 here, C would be 6. So A times C, 5 times 6 is 30. Now I'm going to look for factor pairs that give me 30, but also add together to give me a sum of 17, and that is positive. So with a positive product of 30 and a positive sum of 17, it means both of these numbers would be positive. So I'm going to start with the most obvious thing, since I just multiplied 5 and 6. 5 times 6 obviously is a factor pair that gives 30. But when I add 5 plus 6, I get 11, not 17. So I got to keep looking. Also, 3 times 10 pops out at me, 3 times 10. And when I add those, 3 plus 10 gives me 13. Also not what I'm looking for. I need 17. I didn't try 1 times 30. That would give me 1 plus 30 is 31. That's no good. What about, it's even, so what about 2 times 15? And when I add 2 plus 15, I do get 17. So that works. So here I am going to keep my first term the same and the last term the same and the equal 0 the same. The only thing that's going to change here is I'm going to expand that middle term into 2 terms using these 2 numbers as coefficients. So I'm going to have positive 2x and positive 15x. Now I'm going to group those up into pairs and one by one factor out anything that's common from the, each pair. Excuse me. I've been talking a lot today, doing a lot of recording, so I apologize for my hoarseness. All right, so from the first 2 terms, I'm going to take out x, factor out x, and then I'll have 5x plus 2 left inside the quantity. Then I have from the second pair of terms, I'm going to take out, let's see, a 3. And then 15x divided by 3 is 5x. 6 divided by 3 is 2. Oh, good. Now, this is what we want. This is the thing. You see these quantities matching up, that means everything went according to plan. If not, then you gotta work on it. Something went wrong, or maybe it's not factorable. So 5x plus 2, I'm going to factor that out since it's common, and then multiply that times the quantity with x and positive 3 together. And then from there, you would solve it for x. Let me just double check. Yes, the directions were solved. We're going to take it all the way to the end and find out what values of x would make this equation true. So we will take each factor and set it equal to 0, knowing that whatever answers we find here, they would both work. So I'm going to subtract 2 from both sides of the first equation. Then I have 5x equals negative 2. Then I'm going to divide by 5 on both sides. And then I have x equals negative 2/5. Now from the other equation, I'm going to subtract 3 on both sides. And so I have x equals negative 3. All right, so negative 2/5 and negative 3. That was weird. Let me fix this. You got to get outside of the fraction first using the arrow key, and then you can put your comma to put the other value. Okay, let's go to the next page. I'll see you in the next video.